Well, last Friday was a really tough day for me. Not only was the Zoom not working on that camera, the audio didn't work either. I uploaded it onto YouTube and the audio didn't work. And so yeah, Zach helped me later on to redo the class. Though I did the lecture in 35 minutes. Wow, if I could only always do it that fast. I was purposely going kind of fast to try to make it as fast as possible so that Zach can get to the banquet. But I think it's typically good to go a little bit slower than that. Our main goals today are to look at uniform continuity some more, think about some more examples. To finish chapter 3, section 3.5 is about some miscellaneous topics, including something called what it means for a function to have bounded variation. It's kind of a complicated definition. But I think it's sort of a good preview of thinking about the tough definitions in chapter 5 about integration. And then we are actually going to start chapter 4 on derivatives a little bit today. I will mention, like I mentioned last time, that derivatives do satisfy the intermediate value property, even though they aren't necessarily continuous. A derivative can exist over an entire interval. Okay, it can exist over an entire interval, but fail to be continuous on that interval, but it still satisfies the intermediate value property. And sort of perhaps the simplest example to think about is this one. So this function, which is equal to x squared times sine of 1 over x when x is non-zero, and 0 when x is 0, is a function that oscillates infinitely often in any neighborhood around 0. And the derivative exists everywhere. F prime of 0 is 0 because essentially those oscillations are getting so small in magnitude that the derivative ends up existing, and f prime of 0 does exist and is 0. This is not a proof, but Mathematica says the answer is 0. Ignore the error there. I don't know why it keeps giving me an error here. Not sure. But if you graph the derivative there is the goldish colored one. It oscillates infinitely often as well, but its amplitude does not decay down to 0. The derivative is not continuous at 0, but it does satisfy the intermediate value property on any little neighborhood around 0, and I hope the graph makes it believable. Give me two distinct numbers that have two distinct outputs. Give me any value between those distinct outputs. There's some c such that f of c equals v, that output that's between those values. I hope that makes it believable, the fact that there are infinitely oscillations that don't decay in amplitude there. All right, let's go back to the definition of uniform continuity. And I should emphasize, uniform continuity is not just about the function itself, not just about the formula, but also the domain. So a given function like x squared might be uniformly continuous on some domains, but not others. Some intervals, but not others. And so you have to pay attention to that. You never say this function is uniformly continuous or this one's not without, ideally at least, without specifying the interval you're talking about. So we're given a function defined on some interval, could be defined on a bigger interval too, but it doesn't have to be. We say f is uniformly continuous on I, emphasis not just on the uniformly continuous, but also on I, if for all epsilon greater than 0, what? You can find a delta to make the function outputs within epsilon of each other as long as the inputs are within delta of each other. And that delta works over the entire interval. We're not talking about continuity at just one point C, where C is fixed, and the delta depends on epsilon and C. We're not talking about is f continuous over the interval or not. That's not what we're talking about. That is defined to be the case when f is continuous at every point in the interval. This is something different, something new. adding the word uniformly in there with respect to an interval. For all epsilon greater than 0, there exists a delta greater than 0 such that the distance between f of x and f of y is less than the given epsilon whenever x and y are in the interval and sufficiently close within delta of each other. For all x and y in the interval such that the distance between x and y is less than delta. Our uniform continuity theorem, the thing I said was I called the uniform continuity theorem, is the most fundamental fact about uniform continuity is that if you've got a function that's continuous on a closed and bounded interval, including the endpoints, then it will be uniformly continuous on that same closed and bounded interval. That's the most basic fact to know about uniform continuity. Should be able to prove that, well, linear functions turn out to be uniformly continuous over any interval. Quadratics, for example, end up being uniformly continuous over any bounded interval, open or closed, and in fact you could say the same about any polynomial. Actually, the proof is harder. Though quadratics will not be uniformly continuous over the entire real number line, intuitively it's because the graph ends up growing too fast. If you consider the entire real number line, you can't pick a delta to be the same over the entire interval. So it's continuous over the entire real number line, but not uniformly continuous over. Let's take a look at this example. Prove that f of x equals 1 over x is not uniformly continuous on the open interval from 0 to 1. The book proved it was uniformly continuous on an interval, I believe, of this form, 0.1 to 1 or something like that. The book proved it was uniformly continuous on that interval. But you make that left endpoint 0, it somehow suddenly becomes not uniformly continuous. This is true, we can prove it. Again, intuitively, it's because you got a vertical asymptote at 0, the graph gets too steep. It gets arbitrarily steep as you approach 0. That's the intuition about why it's not uniformly continuous. I think we're only going to have time for scratch work here. So what would you have to do? You have to negate the definition. We've been doing that. Show there exists an epsilon greater than 0 such that for all delta greater than 0, this is not true. This is greater than or equal to epsilon for some x and y in the interval satisfying this condition. There exists an x and y with this condition so that this condition is not true. That's the negation of that definition. What should you pick for epsilon? I got to show there exists an epsilon. Perhaps any positive number will work. That's what you would hope, maybe, to make it as easy as possible. And the typical thing people try is 1. Try letting epsilon equal 1. Scratch work for proof that f of x equals 1 over x is not uniformly continuous on the interval I, that's the open interval from 0 to 1. Try epsilon equals 1. Okay, scratch work. I can put the word try in there. You probably shouldn't put the word try in proofs. Try epsilon equals 1. Let delta be given. You got to show that there exists an epsilon so that for all delta, so the for all goes on the delta, so I have to let delta be given. I want to show this is greater than or equal to epsilon, greater than or equal to 1 for some points in the interval that are within delta of each other, where delta is an arbitrary positive number. I was thinking about this before class. This is not completely obvious what I'm going to say, but it turns out to be good to consider 2 cases. Case 1 delta happens to be greater than or equal to 1. In case 2, delta is less than 1. Case 1 is easy. If delta is greater than or equal to 1, then any 2 points in the interval will be within delta of each other. So then I just need to pick them so that the outputs are bigger than or equal to 1 apart. You could pick 0.5 and 0.25, for example. Let x equal 0.5, y equal 0.25. For example, there's infinitely many choices I could make there. Then 1 over x is 2, 1 over y is 4, and those are greater than or equal to 1 apart. The harder case is case 2, where delta is less than 1. It's positive, but less than 1. You don't know what it is. Could be close to 1, could be 0.999, could be really close to 0, 10 to the negative million power or something. You don't know what delta is. So you need to pick x and y within delta of each other. How are you going to do that if you don't know what delta is? Well, pick something involving delta. Maybe delta and delta over 2. Maybe. In case 2, again, I'll put the word try in here. Try x equals delta and y equals delta over 2. Just seeing if that works. They're certainly within delta of each other. The distance between these is going to be delta over 2. What's 1 over x going to be? It'll be 1 over delta, and 1 over y is going to be 2 over delta. Can you see that down there? Are those more than 1 apart? Subtract them, take the distance, take this one minus that one. 2 over delta minus 1 over delta is 1 over delta. Is that greater than or equal to epsilon, which is 1? Yes, because delta is less than 1 in case 2. So this is greater than 1, which is the epsilon. Take 30 seconds to look over this and think about it again.
Can you explain the negation of this again?
Yeah. To show a function is not uniformly continuous, you've got to negate the for all there to show there exists an epsilon greater than 0. Such that for all delta, no matter how small, the no matter how small is just an extra thought comment. It doesn't have to be true, delta could be big. There exists an x and a y in the interval satisfying this condition, so this one's not satisfied. Try epsilon's 1, hope it works, let delta be given. Find an x and y. In case 1, I picked this for x and y, but I could have picked other numbers. They're within delta of each other because delta is greater than or equal to 1 in this case. And their outputs are 2 apart, actually, bigger than or equal to 1. Case 2, I tried these two, hoping it would work. And we were fortunate, it did work. When I calculate these things, I see that they are more than epsilon apart, the function outputs. In a graph, got a vertical asymptote over here. If delta, let's just pretend delta is 0.01, maybe 0.1. Delta is 0.1 is going to be right there. Delta over 2 is 0.05 in that case. The function outputs are 1 over delta apart. 1 over delta would be 10. I didn't draw it very well, but this output's supposed to be 10 away from the other output. Look at another example. Prove that sine of x squared is not uniformly continuous on R. Actually, sine of x is uniformly continuous on R, the entire real number line, just a sine of x. Intuitively, it's because the slopes don't get arbitrarily large, so I keep referring to the slopes here, Uniform continuity can be thought of in terms of derivatives when the function is differentiable. Actually, the uniform continuity of the sine function over the entire real number line can be proved with that inequality used to prove that sine of x was continuous everywhere. The uniform continuity over the entire real number line can be proved with the same inequality, this one. The fact that for any x and y, the distance between sine of x and sine of y is less than or equal to the distance between x and y themselves. That was a fact we used back last week. And it's useful not just for proving continuity everywhere, but uniform continuity over the entire real number line. But if I put a square in there on the x, consider sine of x squared, I claim that's not uniformly continuous over the entire real number line. Of course, it is uniformly continuous over any closed and bounded interval by the uniform continuity theorem. What's going on there? The fact that you've got an x squared in there makes the graph oscillate more and more rapidly as x gets bigger. And the slopes do get arbitrarily large, so the delta won't work. The same delta won't work over the entire real number line is the intuition there. It'll work over any finite interval, even though the slopes can get really high. But over the entire real number line, it won't. How would you prove that? Once again, I'm not going to prove it in complete detail, but let's think about the scratch work and what might be necessary for the proof. Sine of x squared is the function. The interval is the entire real number line. The fact about the slopes getting arbitrarily large is not a proof, but it would give you the intuition, if you think about this stuff enough, that it's probably not uniformly continuous on the entire real number line. So once again, I got to find an epsilon such that for any delta, there's some x and y in the entire real number line where this is not true. Once again, you could try something for epsilon like 1. Try epsilon equals 1. Will 1 always work? Not necessarily. And in fact, if we were trying to prove the function 0.1 times sine of x squared was not uniformly continuous over the entire real number line, we'd want to use a smaller epsilon. The amplitude would be smaller, and the outputs would always be less than 1 apart. So 1 wouldn't work in that case. 0.1 would work. The amplitude was 0.1. Okay, so 1 doesn't always work. It does depend on the situation, but it'll work here. What do we need to do? We need to think about, well, let's just think about the picture first here. Oscillates faster and faster. Give me an arbitrary delta. I want to find 2 points x and y within delta of each other so that the distance between their outputs is greater than or equal to 1. Seems to me to maybe be good to focus on, I could pick points that happen to reach a maximum value, and I could pick points that happen to be x-intercepts, or reach a minimum value. The outputs there are 2 units apart, greater than or equal to 1. If I could, based on the given delta, choose x and y to be within delta of each other to make the where these oscillations are also sort of within delta of each other. Each oscillation is within delta of the next oscillation horizontally. That should do it. I know the sine function will equal positive 1 when the input is pi over 2 plus some integer multiple of 2 pi. This will be when x squared equals pi over 2 plus some 2n pi, where n is an integer. And that's going to happen when, at least for positive values of x, x is square root of pi over 2 plus 2n pi, where n again is a positive integer. That equals 1, right? And sine of x squared will equal negative 1 when x is negative pi over 2 plus 2n pi. Or, if you prefer, 3 pi over 2 plus 2n pi. When x is square root of 3 pi over 2 plus 2n pi for some integer n. So the real question is, can I choose n so that these are within delta of each other? Can these be made arbitrarily close for large n? I'm not going to prove it, but I want to come essentially do a limit calculation to help you believe it. Take a look at these expressions. Let me do the 3 pi over 2 on the left, and the one involving pi over 2 on the right, and I'm going to subtract them. I'm wondering if this difference can be made arbitrarily small by making n sufficiently large. And through a bit of trickery, here we go, memorize trickery. Multiply the top and the bottom of this by, well, okay, is there a bottom? Well, sure, one. Multiply the top and the bottom of it by the same thing except with a plus sign. This common trick. It's not clear that it's going to be helpful. But in this kind of situation, it's kind of the only thing you can try. That seems like it might have a chance of being helpful. It's going to get rid of the square roots on top. After you FOIL it out, the outside and the inside terms cancel. You still have the square roots on the bottom, but that's okay. You do get some cancellation of the terms involving n on top, and that's the key to seeing this work here. I'm not going to prove this converges to 0 as n goes to infinity, but I hope you believe it looking at the formula here. Is that dark enough to see? Zoom in if you need to. Constant divided by this, then goes to infinity. That's going to go to 0. I'm not proving that, but I hope it's believable. I could prove it, I think, but it would be a bit of a pain. So once you know this goes to 0 as n goes to infinity, you can choose values of n large enough to make this difference less than the given delta. Delta is positive. We've just seen that this goes to 0. So without saying what n is, I believe, I'm looking at this and saying, I believe in my heart and in my mind that I can choose n sufficiently large to make this less than delta, meaning they're within delta of each other. And their outputs are 2 apart, 1 and negative 1 are 2 units apart, bigger than or equal to 1.
So according to the definition, are the square root of pi over 2 plus 2 and pi, and the other one with the 3 pi, are those both like the x and y?
Yeah.
Okay.
This would be x and this would be y, or vice versa.
Okay.
Yep. I wrote two x's here, but that's just because I was thinking about solving those equations.
Okay.
So we can always just switch them however we want to make it work.
Well, yeah, the roles of x and y are symmetric. It doesn't matter which one's x and which one's y. Is that what you're asking?
Yeah,
Yeah.
so you have absolute value.
Yeah.
around it,
I'm not saying which one's bigger. I mean, I did write this, so that this is definitely bigger than that. But as far as which one's x and which one's y, it doesn't matter. So, uniform continuity it's a pretty challenging topic, I think. Anything with epsilons and deltas, you could say is challenging. But I think we've hit the most fundamental things about it. Our main use of uniform continuity comes in chapter 5. It allows us to prove that continuous functions are integrable, Riemann integrable, we say. You can integrate them on any closed and bounded interval because they will also be uniformly continuous on that interval, and that's the key to making a proof work. That's our main application of the uniform continuity. The last section of chapter 3 is about some miscellaneous topics. The first group of topics can be summarized in that statement. Monotone functions are, quote unquote, nice. What does nice mean? Well, one-sided limits exist at every point. That's definitely not the case for non-monotone functions in general. Think of the function that's 0 for all irrationals and 1 for all rationals. Then two-sided limits don't exist, and also one-sided limits don't exist everywhere. Believe that? The function that's always 0 when you plug in rational or irrational, say, and always 1 when you plug in rationals. Definitely not a monotone function. Not continuous, limits don't exist, not even one-sided limits. But with monotone functions, whether they're monotone increasing or monotone decreasing, they always have one-sided limits. They can fail to have two-sided limits. Can have jump discontinuities with monotone functions. Got something like that, the two-sided limit would fail to exist at that point. But one-sided limits do exist. By the way, I haven't written this in class, but it is in the book. There's kind of a funny notation involved with one-sided limits. The left-hand limit at C here would be written f of C minus. That's not a function value. Second coordinate at that point's not on the graph. F of C minus, by definition, is just another notation for the left-hand limit at C. Here we put the minus there. I guess I'm used to putting this minus up there as if it's an exponent. It's not an exponent. Maybe it's better to put it there. I think here it's typically down a little further in the notation. Here, this value, the right-hand limit, is written f of C plus. And, well, that does happen to equal the function value at C, but it didn't have to. I could have a jump discontinuity like that, and this would be the value f of C itself. So those left and right-hand limits exist everywhere on the domain of a monotone function, continuous or not. If you consider the set of all points where a monotone function is discontinuous, that set is countable, either finite or countably infinite. It can't be uncountable. The intuition there is the only kinds of discontinuities that occur are jump discontinuities. And so you sort of can't have too many jump discontinuities for a monotone function that's defined over a closed interval. We are talking about closed intervals here. The function is defined. They are differentiable. They have a derivative almost everywhere. What does that mean? Well, I'm not really going to say what that means. talk about sets of measure 0. And we're not going to get into that. That's a pretty advanced concept. But you could sort of just say in your mind, okay, they are continuous at lots and lots of values of x compared to where they're not continuous. Might be just the most basic intuitive approach to that statement. And we will see in chapter 5 that they are Riemann integrable. We can integrate them. That doesn't mean you can necessarily use the fundamental theorem of calculus, by the way. Although it turns out you can with monotone functions on closed intervals. But at the outset, it doesn't necessarily mean that. It means that the limiting process we'll talk about in chapter 5, the limit will exist in that limiting process for monotone functions. We'll be talking about limits of Riemann sums, like you do in Calc 2, though we will be approaching it from a more general perspective. Is integrable synonymous with Riemann integrable? Actually, no, I might have mentioned this the first day or two of class. There are actually other kinds of integrals you can do, other kinds of integration theories, the most common of which is called Lebesgue integration. That's how you spell Lebesgue. It's not Lebesgue, Lebesgue. That's what you say. Lebesgue integration is another common kind of integration. There's actually others too beyond those. Why would you have different kinds of integration theory I'm talking about? Essentially because some frameworks work better than others in proving certain things. They also, Lebesgue integration is more general than Riemann integration. You can integrate more functions, so to speak. There are functions which are not Riemann integrable. In fact, that one that's 0 at all irrationals and 1 at all rationals is not Riemann integrable. You can't integrate it according to Riemann's definition, but you can integrate it according to Lebesgue's. So it's more general in that sense too. So there are these facts to know about monotone functions, and you should know those for exam 2. That's just facts to know. You could be, have multiple choice or true/false questions related to them. As far as the homework due on Wednesday, you will be modifying one of the proofs of one of those, so you'll be studying that proof, and you will be also thinking about some examples related to another one. What I think is more important to spend more time on, though, is an even harder concept, and that's called the variation of a function and something related, functions of bounded variation. This is a pretty tough topic. If you've finished reading chapter 3, you know what I'm talking about. You know it's tough. If you force yourself to struggle through it. We're not going to certainly prove much here, but I do want to talk about the definition and an important calculational tool related to this for functions that are either monotone or don't oscillate infinitely often. So they're relatively nice. So we're going to be given, here's the framework, we're given a closed and bounded interval.
Is this for both, or are we focusing?
It's for both, really. I got to first define the variation of a function, and then I can define what it means for a function to have bounded variation. A function whose domain is I, and I got also a subinterval of I. So C and D are between A and B. It's implicit here that A is less than B and C is less than D. I Actually, before I can define the variation of a function, I need another preliminary definition. A partition of the interval from C to D. Our book takes to be a set of points where the first point is the left endpoint C, the last point is the right endpoint D, and all the other points in between, well, they are in between and you list them in order. I use set notation here, so technically speaking, the set notation doesn't imply that they're in order here. It's a set such that, I guess I started at 0, sorry. 0, 1, 2, 3, etc. C is x0, which is less than x1, which is less than x2, less than x3, etc. The last one, x sub n, is equal to the right endpoint, D. This is different than a partition in algebraic structures, though kind of similar. A partition in algebraic structures, I hope you remember, is a collection of disjoint sets whose union is the entire group, for example, if you're partitioning your group. Remember when you did partitions of groups, that was for cosets to construct fact groups. Are these always bad memories?
No, that's pretty fun.
Okay. You can partition groups into disjoint sets whose union is the entire group. You could consider partitions like this as breaking the entire interval into subintervals. The union is the entire interval, though they're not disjoint, because the endpoints overlap. The right endpoint of the first interval, right there, x1, becomes the left endpoint of the second interval. So technically speaking, they're not disjoint, but they're almost disjoint. So it's a similar idea. Although here we're not talking about the partition being the sets themselves, but the points, the endpoints. So in that sense, it's also different. That's our framework. This symbol V of f, comma, the interval CD is the symbol used for a quantity called the variation of f over the interval from C to D. It's defined to be the soup of a collection of values where those values are summations, I goes from 1 to n, of differences, of absolute values of differences of this form. Where this soup, the supremum, is kind of a complicated thing. It's the supremum over the set of all sums like this over all possible partitions of the interval. That's a lot to get your mind around. This is over all such partitions of the interval. For any given partition of the interval, you can compute the sum. Now do it for all possible partitions of the interval. N can be anything too, because your partition could have 3 points in it, or it could have a Google points in it, 10 to the Google power, that's a Googleplex. With the Googleplex factorials, it can be huge. what n is here. I'm considering all possible summations I could make it like this to get a bunch of different values and then take the soup. Now that soup is not necessarily finite. This could be infinite. So it's a soup in the extended sense. If the collection of all such numbers is not bounded above, technically speaking, the soup doesn't exist. But we can, in an extended sense, call this infinity if this set is unbounded. That's called the variation of the function. Pretty complicated definition. It's actually a very simple concept for monotone functions, for example. Where should I draw my picture here? I guess we'll go over here on the left side. You got a monotone function, could have some jump discontinuities. Say the graph looks like that. Turns out the variation equals, in this picture, f of d minus f of c. The variation of this function over this interval is f of d minus f of c, and it's actually not hard to prove because for any partition of that interval from c to d, when you do this kind of summation, you're going to get the exact same answer. That's what's going to happen with monotone functions like this. First of all, because I've made it monotone increasing, I can just get rid of the absolute value signs. So that's because f, in my picture here, I'm assuming f is monotone increasing. If it was monotone decreasing, I could get rid of the absolute value signs as well, though I'd have to switch around the order of the difference. And no matter what the x's are, this is a telescoping sum. You get a bunch of cancellation. This is f of x1 minus f of x0 plus f of x2 minus f of x1 plus f of x3 minus f of x2, etc. The second to last one would be f of xn minus 1 minus f of xn minus 2. And the last one would be f of xn minus f of xn minus 1. And a bunch of stuff cancels. This cancels with that. This cancels with that. This cancels with something that I didn't write. This cancels with this. This cancels with something